Welcome to this presentation, where we will be diving deep into section 14.2 of our course, which is focused on using the linear model. As we move through this section, our primary goal will be to understand how to determine if there is a linear association between two variables and how to make informed inferences based on this association. Let's begin by considering a scenario where we have two variables, and we suspect that they are related to each other in a linear fashion. For instance, think about the relationship between the amount of time spent studying and the scores achieved on a test. Intuitively, we might expect that as study time increases, test scores should also increase. But how can we be sure that this relationship is indeed linear? How do we quantify this relationship? And more importantly, how do we test if this relationship is statistically significant? This is where the linear model comes into play. The linear model helps us to not only establish the relationship between two variables, but also to test if this relationship is significant enough to be of interest. In this section, we will learn how to perform a hypothesis test to determine if there is indeed a linear association between two variables. This process will involve setting up null and alternative hypotheses, calculating a test statistic, and ultimately deciding whether or not we have enough evidence to reject the null hypothesis. But we won't stop there. Once we have established that there is a linear relationship between our variables, we also need to quantify this relationship. This is done by constructing confidence intervals for the intercept and slope of the linear model. These confidence intervals will provide us with a range of plausible values for the intercept and slope, helping us to understand the precision of our estimates and the reliability of our model. Throughout this section, we will be using real-world data examples to illustrate these concepts. By the end of this section, you should feel confident in your ability to use the linear model to explore the relationships between variables, to test hypotheses about these relationships, and to construct and interpret confidence intervals for your regression coefficients. So, let's get started by delving into the details of the linear model and how it can be used to make powerful inferences about the world around us. Now, let's talk about an important concept in regression analysis: the difference between population values and estimates. When we talk about population values in the context of regression, we're referring to the true values of the intercept and slope that would result if we could measure every single member of the population with perfect accuracy. These true values are often elusive because in practice, we rarely have the resources or ability to collect data from an entire population. Imagine, for example, trying to measure the relationship between years of education and income for every single person in a country. It would be an enormous, if not impossible, task. Because we can't usually measure an entire population, we instead collect a sample, which is a smaller, manageable subset of the population. From this sample, we calculate estimates of the intercept and slope. These estimates are our best guesses of what the true population values might be. However, it's important to remember that these estimates are based on the sample data, and thus they might differ from the true population values. In statistical terms, the true population values are called parameters. These parameters are what we aim to learn about or make inferences about using our sample data. The values we calculate from the sample data are called estimates or statistics. For instance, if we collected data on a sample of people's education levels and their incomes, we could use this data to estimate the slope of the relationship between education and income. This estimated slope gives us an idea of how much we might expect income to increase with each additional year of education. But it's crucial to understand that this estimate might not be exactly the same as the true slope in the entire population. Our job in regression analysis is to make these estimates as accurate and reliable as possible. We use various statistical techniques like confidence intervals and hypothesis tests to assess how close our estimates might be to the true population values. This process helps us make informed decisions based on our data, even though we are working with only a sample. Understanding the difference between population values and estimates is fundamental in statistics. It reminds us of the inherent uncertainty in our estimates and the importance of using sound statistical methods to account for this uncertainty. By acknowledging this distinction, we can better interpret the results of our analysis and understand the limitations of the conclusions we draw from our sample data. Let's now turn our attention to the specific notation used in regression analysis, which is crucial for understanding and communicating the results of our linear models. In regression analysis, we often deal with two key components, the intercept and the slope. These elements define the line that best fits the data. We use specific symbols to represent these components, and it's important to understand what each symbol stands for. First, let's talk about the intercept. The intercept is the point where the regression line crosses the y-axis. It represents the expected value of the dependent variable, y, when the independent variable, x, is 0. We denote the true population intercept with the symbol beta 0. This is the actual intercept we would observe if we had access to data from the entire population. Next, we have the slope, which tells us how much the dependent variable, y, is expected to change with a 1-unit increase in the independent variable, x. The true population slope is represented by beta 1. This slope indicates the strength and direction of the linear relationship between x and y. However, as we discussed earlier, we rarely have data for the entire population. Instead, we work with sample data, and from this sample, we calculate estimates of the intercept and slope. These estimates are our best guesses for the true population values. The estimator of the population intercept is represented by hat beta 0. This is the value we calculate from our sample data, and it serves as an estimate of beta 0, the true intercept. Similarly, the estimator of the population's slope is represented by hat beta 1. This is the slope calculated from our sample, and it serves as an estimate of beta 1, the true slope. Finally, we have the predicted value of y higher, which is denoted by hat y. This value represents the expected value of the dependent variable for a given value of the independent variable according to our regression model. Essentially, hat y is the value that lies on our estimated regression line for a given x. In summary, beta 0 represents the population intercept. Beta 1 represents the population slope. Hat beta 0 represents the estimator of the population intercept. Hat beta 1 represents the estimator of the population slope. Hat y represents the predicted value of y based on our regression model. Understanding this notation is essential for interpreting the results of regression analysis and for effectively communicating these results to others. As we proceed through this section, we'll use this notation frequently, so it's important to be familiar with these symbols and what they represent. Now that we've familiarized ourselves with the notation, let's move on to the equation of the regression line, which is the backbone of any linear regression analysis. Using the notation we just discussed, the equation of the regression line is written as hat y equals hat beta or 1x. Let's break this down. Let's for hat y, Steph represents the predicted value of the dependent variable y based on our model. Hat beta is the estimated intercept. This is the value of y when the independent variable x is 0. It's the point where the regression line crosses the y-axis. The per strength is the estimated slope of the regression line. It tells us how much y is expected to change with a 1-unit increase in x. X is the independent variable, the variable we're using to predict y. This equation forms the basis for predicting values of y, given specific values of x. For example, if we're studying the relationship between hours studied and exam scores, x would represent the number of hours studied, and hat would represent the predicted exam score for a given number of study hours. In practice, generating this equation typically involves using statistical software. The software takes your data and applies a method, usually least squares regression, to find the best fitting line through the data points. The output from the software provides the values of hat beta 0 and hat beta 1, which you then use to write your regression equation. However, it's not enough just to generate the regression equation. As data analysts or researchers, We must interpret the results and evaluate the conditions under which our linear model was constructed. This involves checking assumptions like linearity, independence, and homoscedasticity, constant variance of errors, among others. These conditions are crucial because if they don't hold, the results we obtain from our regression model might be misleading or incorrect. Therefore, after obtaining the regression equation, we need to carefully interpret the output and consider whether the conditions for the regression model are sufficiently met. Only then can we confidently use the linear model to learn something meaningful about the relationship between the variables in question. Understanding and correctly applying this equation is essential for making predictions and drawing valid conclusions from our data. As we move forward, we'll see how this equation is used in hypothesis testing and constructing confidence intervals, allowing us to make informed inferences based on our linear model. Let's now discuss two essential facts about estimators in the context of regression analysis, which are crucial for understanding the reliability and accuracy of our estimates. 1. The sampling distribution of the estimators follows the normal model. When we talk about estimators, we're referring to the values we calculate from our sample data, like the estimated slope and intercept in our regression model. Now, even though these estimates are based on a single sample, they are not fixed. If we were to take multiple samples from the population, each sample would likely produce slightly different estimates for the slope and intercept. The distribution of these different estimates across many samples is what we call the sampling distribution. One of the most important properties of this sampling distribution is that it tends to follow a normal distribution, especially as the sample size becomes larger. This normality is a key assumption in many statistical procedures, including constructing confidence intervals and conducting hypothesis tests. It allows us to make probabilistic statements about how far our sample estimates might be from the true population parameters. 2. The estimators are unbiased. Typically, our calculated values for the intercept and slope, based on our data, will be about the same as the population values. An estimator is said to be unbiased if, on average, it produces the true population parameter. In simpler terms, if you were to repeatedly take samples and calculate the slope or intercept each time, the average of those estimates would be equal to the actual slope or intercept of the entire population. This property of being unbiased is crucial because it means that our estimates are reliable in the long run. When we calculate the intercept and slope from our sample data, we can be reasonably confident that these estimates are close to the true population values. Of course, any single estimate might be slightly off due to random sampling variability, but on average, our method gives us the correct values. These two facts, the normality of the sampling distribution and the unbiasedness of our estimators, provide a solid foundation for the inferences we make using linear regression. They give us confidence that the procedures we use to estimate and test relationships in our data are valid and that our conclusions are likely to be accurate. Understanding these concepts is vital for interpreting the results of your regression analysis and ensuring that the decisions you make based on your data are well-grounded. Now, let's explore how we test the significance of the intercept and slope in our regression model by focusing on the test statistic used in hypothesis testing. When we want to determine if our estimated intercept or slope significantly differs from a hypothesized value, often 0, we perform a hypothesis test. The core of this test lies in the calculation of the test statistic, which helps us decide whether to reject the null hypothesis. The test statistic for both the intercept and the slope has a familiar and straightforward form. T equals fraxt estimator, text null value, text E. Let's break down what each part of this formula represents. Estimator. This is the value we have calculated from our sample data, either the estimated intercept, beta 0, or the estimated slope, hat beta 1. Null value. This is the value specified by the null hypothesis. In many cases, particularly for the slope, the null hypothesis states that the parameter is 0, implying no effect or no relationship. Therefore, the null value is often 0, but it can be another value depending on the hypothesis being tested. SE, standard error. The SE in the denominator stands for the estimated standard error of the estimator. It quantifies the variability of the estimator, how much the estimated value might vary from sample to sample. A smaller standard error indicates that our estimate is more precise. The result of this formula gives us the t-statistic, which tells us how many standard errors the estimator is away from the null value. A large absolute value of the t-statistic suggests that the estimator is far from the null value, providing evidence against the null hypothesis. For example, if we're testing whether the slope hat beta 1 is significantly different from 0, we'd use the formula to calculate the t-statistic based on our sample data. If the t-statistic is large enough in absolute terms, we might conclude that the slope is significantly different from 0, implying a linear relationship between the independent and dependent variables. This test statistic is crucial because it allows us to quantify the evidence against the null hypothesis and make informed decisions based on our data. It's a fundamental tool in regression analysis for assessing the significance of our model parameters and, ultimately, for determining the strength and validity of the relationships we're studying. When conducting hypothesis tests for the slope in regression analysis, it's important to clearly define the hypotheses we are testing. Typically, statistical software automates this process, generating the hypotheses and performing the test for us. Let's take a closer look at the common hypotheses involved in testing the significance of the slope. 1. The slope equals 0. Mathematically, this is expressed as h0 beta 1 equals 0. The null hypothesis posits that there is no relationship between the independent variable x and the dependent variable y. In other words, it suggests that changes in x do not result in any changes in y, and the slope of the regression line is 0, meaning the line is perfectly horizontal. 2. Alternative hypothesis, HA, the slope does not equal 0. This is expressed as HA beta 1 neek 0. The alternative hypothesis suggests that there is indeed a relationship between the independent variable x and the dependent variable y. This implies that the slope of the regression line is not 0, indicating a linear association between the two variables. In some contexts, particularly when considering the broader relationship between variables, we might instead frame the hypotheses in terms of correlation. H0 star, the correlation is 0. This hypothesis suggests that there is no linear association between the variables. The correlation is not 0. This hypothesis indicates that there is a linear association between the variables. These hypotheses are foundational to the process of testing whether the independent variable has a statistically significant effect on the dependent variable. If the data provides enough evidence to reject the null hypothesis, we conclude that the slope is significantly different from 0, indicating a linear relationship between the variables. The outcome of this hypothesis test helps us decide whether the independent variable is a meaningful predictor of the dependent variable. If the slope is significantly different from 0, it suggests that changes in the independent variable are associated with changes in the dependent variable, validating the use of the linear model for prediction and inference. Let's apply what we've learned so far by looking at a practical example involving eBay auctions. This example will help us understand how to perform and interpret a hypothesis test for a linear regression model. In this scenario, we want to determine if there's an association between the number of people who bid on an item and the final cost of that item. Specifically, we're looking at data collected on the number of bids, denoted as n bids, and the total price of the item, denoted as total PR, for sales of a popular video game, Mario Kart. Our task is to state the null and alternative hypotheses, calculate the test statistic, determine the p-value, and ultimately make a conclusion based on this information. The goal is to find out whether the number of bids placed on an item has a statistically significant impact on the final price of the item. Before we proceed, let's assume that the conditions for the linear regression model are satisfied. This means we're confident that the linear model is appropriate for this data and that any assumptions underlying the model, such as linearity, independence, and constant variance, hold true. Now, let's outline our hypotheses. Null hypothesis, H0. The slope beta 1 equals 0, meaning there is no linear association between the number of bids and the final price. Mathematically, this is expressed as H0 beta 1 equals 0. Alternative hypothesis. The slope beta 1 does not equal 0, indicating that there is a linear association between the number of bids and the final price. This is expressed as HA beta 1 equals 0. Using the data provided, we will calculate the test statistic, which measures how far the sample estimate, the slope calculated from the data, is from the null value, which is 0 in this case, relative to the standard error. We will also calculate the p-value, which tells us the probability of observing the data we have, or something more extreme, if the null hypothesis is true. Finally, based on the p-value and a predetermined significance level, often 0.05, we will decide whether to reject the null hypothesis. If the p-value is small enough, we will reject the null hypothesis and conclude that there is a significant association between the number of bids and the final price. If the p-value is large, we will not reject the null hypothesis, suggesting that the number of bids may not significantly affect the final price. In the next slide, we will look at the specific results from this analysis, including the test statistic and p-value, to make our final conclusion. Let's now take a closer look at the results from our eBay auction example, as presented in the output from the statistical software. We began with the following hypotheses. Null hypothesis H0, the slope beta 1 equals 0, meaning there is no linear association between the number of bids and the final price of the item. Alternative hypothesis, HA, the slope beta 1 equals 0, indicating that there is a linear association between the number of bids and the final price of the item. The software provides us with a variety of statistics that are key to making our decision. Test statistic T. The calculated t-value is minus 0.931. This value tells us how far our estimated slope, hat beta 1, is from the null value, which is 0 in terms of standard errors. The p-value associated with this t-statistic is 0.3534. The p-value is the probability of obtaining a test statistic at least as extreme as the one observed, under the assumption that the null hypothesis is true. Given that the p-value is 0.3534, which is much greater than the common significance level of 0.05, we do not have sufficient evidence to reject the null hypothesis. This means we fail to reject H0. Based on these results, there is not enough evidence to conclude that the price of items is associated with the number of bids placed on the item. In other words, the data does not support a significant linear relationship between the number of bids and the final price in this case. This example illustrates how we can use hypothesis testing to explore potential relationships between variables. Despite our initial assumption that more bids might drive up the price, the data does not provide strong enough evidence to support this claim. Therefore, we must conclude that, at least based on this dataset, the number of bids does not significantly affect the final sale price of the items. Now let's discuss confidence intervals for the intercept and slope in regression analysis. Confidence intervals are essential tools that allow us to estimate the range within which the true population parameters are likely to fall, given our sample data. The confidence interval for either the intercept or the slope follows a familiar form. Text estimate PMT. Here's what each part of this formula represents. Estimate. This is the point estimate we obtained from our sample data, either the estimated intercept, hat beta 0, or the estimated slope, hat beta 1. This T. This is the critical value from the t-distribution corresponding to the desired confidence level, such as 95%. The t-value is determined based on the degrees of freedom associated with the estimate. This stands for the standard error of the estimate, which quantifies the variability of the estimate due to sampling error. The standard error is typically provided by the statistical software along with the estimate. The confidence interval is calculated by taking the estimate and adding and subtracting the product of the t-value and the standard error. This results in a range that we are confident contains the true population parameter with the specified level of confidence. e.g., 95%. Most statistical software will automatically generate confidence intervals for both the intercept and slope when you perform a regression analysis. These intervals give us a range of plausible values for the population intercept and slope, providing valuable context for interpreting the point estimates. For example, if the confidence interval for the slope does not include 0, it suggests that there is a significant linear relationship between the independent and dependent variables. On the other hand, if the interval does include 0, it indicates that the slope might be 0, implying that the independent variable may not have a significant effect on the dependent variable. In summary, confidence intervals are crucial because they offer a range of values within which the true population parameters are likely to lie based on our sample data. This allows us to quantify the uncertainty around our estimates and make more informed decisions based on the analysis. As we interpret our regression results, these intervals will help us understand the reliability and precision of our model's predictions. Let's continue with our eBay auction example by interpreting the confidence intervals provided for the intercept and slope. Tashtahar 95% confidence interval for the intercept. The output gives us a 95% confidence interval for the intercept, which ranges from 45.2 to 52.9. This means that we are 95% confident that the true intercept of the population regression line lies between these two values. In other words, if we were to take many samples and compute the intercept for each one, 95% of those intervals would contain the true population intercept. 95% confidence interval for the slope. The 95% confidence interval for the slope is given as Thyngena's 0.39, 0.14. This interval tells us that we are 95% confident the true slope of the population regression line lies somewhere between Thyngena's 0.39 and 0.14. However, there's a crucial point to notice here. The confidence interval for the slope includes 0. This inclusion means that it is possible the true slope could be 0, implying that there may be no linear association between the number of bids and the final price of the item. This result aligns with our previous finding, where we failed to reject the null hypothesis in the hypothesis test. Conclusion: given that the confidence interval for the slope includes 0, we must consider the possibility that there is no association between the number of bids and the final price of the item. This interval-based interpretation supports the earlier hypothesis test result, reinforcing the conclusion that the number of bids may not significantly impact the final price in this dataset. Confidence intervals provide a range of plausible values for the intercept and slope, helping us understand the precision of our estimates and the uncertainty associated with them. In this case, the confidence intervals suggest that while the intercept is well defined, the slope could be close to 0, indicating a weak or non-existent relationship between the variables under study.